Good afternoon. And today I'm going to talk about near Earth space and Sun Earth connection. My name is Dibyende Chakrabarty. I am from Physical Research Laboratory, Ahmedabad. And today's topic is based on space weather and near Earth space environment. So initially I thought that maybe it will be better to talk about what exactly do we mean by space? What is the technical or operational definition of space? In operational terms, we generally call Kármán line, which is around 100 kilometers above the Earth's surface, which is the line, which is a hypothetical line that separates the atmosphere and the space. Because at this height, the speed needed to achieve lift or net upward force in the thin atmosphere, because as you know, the density as you go up is going down. As we are going up in altitude, the density is going down, and therefore you require the atmospheric thrust that a vehicle needs to generate in order to remain afloat. That becomes very, very difficult to attain at a atmosphere which is very, very thin, and therefore the speed at which the vehicle has to move, it has to be very, very fast, and that is the line that we call it Kármán line. So beyond that, that's what is written here, that the switching from the steering with thruster to maneuvering with aerodynamic control. That means if you cross the Kármán line, we require thruster control in order to navigate a spacecraft. And if you come down, cross the Kármán line, technically speaking, operationally speaking, you have a thicker or denser atmosphere, and therefore you need an aerodynamic control surfaces to navigate through the atmosphere. So this is the operational definition of atmosphere and space. So in today's talk, because I'll be talking about space weather or near Earth space, I'll be mostly talking about regions which are above 100 kilometers or so. Now, what is space weather is that we know about the terrestrial weather at the ground, where we have rainfall, we have wind speed, we have cyclones. These are terrestrial weather. These happens at a very low height of the atmosphere, which we call troposphere. But space weather is anything that happens above 100 kilometers. Whatever space environment we have, there any kind of disturbances at a time scale which is of the order of minutes, hours, or days, those are considered to be space weather disturbances or space weather fluctuations. And when we talk about the upper atmosphere or space environment of the Earth, it is basically governed by the sun, which is shown by this hue graph. And you can see that different solar disturbances, some of them are called coronal mass ejection, some of them are called solar flares, which are coming from the brightening of the solar. Some part of the solar disk, it gets brightened up. There are massive explosions on the solar surface and resulting into very high energetic radiations that are coming towards the Earth. And coronal mass ejections are actually physical expulsion of coronal masses towards the Earth. These are magnetized, and you know that Earth is a magnetized planet, and the interaction between this coronal mass ejection structure and the Earth's magnetic field can create turbulence in our outer space environment. In addition to that, there is solar wind, which is continuously coming from the sun, which are charged particles that are coming from the sun, which primarily consist of protons and alpha particles. Now, when you say space weather, and on the right hand side, you see there are magnetic field lines that is encircling the Earth. Up to a certain distance, the magnetic field lines are closed and they co-rotate with Earth. And beyond that distance, you can see that magnetic field lines can get opened up because of the interaction with the magnetic field that is coming from the sun. And if they are of opposite polarity, they can open up the Earth's magnetic field and giving direct entry of solar wind particles or magnetic field disturbances in the higher heights of the Earth. That is the near Earth space or geospace. That's how we call it. Now, if you look at this picture carefully, you will see on the day side the magnetosphere, which is the outer part of the Earth's atmosphere. You can see here it is magnetosphere. It is compressed because of the solar wind. And on the night side of it, which is the opposite side of the sun, magnetosphere is elongated to a very, very high distance. If I give you a rough idea of the scale that I'm talking about, the moon is at a distance of 60 Earth radii, and magnetosphere can go up to 100 Earth radii. One Earth radii is around 6,300 kilometers or so. And on the day side, this distance is around 10 to 12 Earth radii or so, which can change depending on the solar conditions. Therefore, moon is here, and it can come out in the nearer space and then come out and go into the magnetosphere as it orbits around the Earth. So this is the space environment that we are living in, and therefore it's of utmost importance that every solar disturbances will have a repercussion on the kind of disturbances that we see on the upper part of our near space environment. So we define the space weather in the following way. The term space weather refers to conditions on the sun and in the solar wind, magnetosphere, ionosphere, and thermosphere that can influence the performance and reliability of spaceborne and ground-based technological systems, and that can affect human life and health. This is what happens. This is a movie that shows what happens grossly, when you call that space weather disturbances has taken place. You see the solar wind is coming from the sun. This is the sun, and this solar wind travels through the interplanetary medium. It has magnetic field embedded into it, and as it comes closer to the Earth, if the solar wind magnetic field is of opposite polarity to that of the Earth's magnetic field, it can open up the magnetic field, and as solar wind is moving on the other side, it can drag the magnetic field to the night side, and then the night side magnetic field can actually reconnect here, and then creating an explosion which forces charged particle to follow magnetic field and come to the polar region, creating aurora. This is aurora borealis around the North Pole, and this is aurora australis in the South Pole. And this is how mostly the auroras are created on the night side. So aurora is a consequence of the space weather events or space weather disturbances that happen in the near Earth space. One way to look at aurora is that if you go to the polar region, very close to the poles, you see auroras, or if you are in International Space Station, you can see aurora at a lower height as well, because the space station is flying at around 400 kilometers or so, and you can see these auroras are at a slightly lower height. And as you go along the polar region, you see these green and red auroras that are coming in the sky. And this is because of the charged particle hitting the atmospheric atoms and molecules, exciting them. And when these atoms and molecules are getting de-excited, it is actually creating a faint emission, which is detectable. Now, in addition to this aurora, there is something called air glow emission, which is there throughout the globe. And it is because of solar radiation can always excite the atoms and molecules on the atmosphere. It can excite them, and when it de-excites, it gives up emissions at different heights, and by different species when it is coming, it gives up different colored emission. This is very faint, and you require special instrumentation to measure this kind of emissions. And if you can measure these emissions, you can know the health of the near Earth space around us. And that is one of the techniques the scientists use to actually infer about the state of the ionosphere and the upper atmosphere, or the near Earth space, the way you call it. Not only on Earth, you see aurora on other planets as well. You see aurora in Saturn here, you see aurora on Jupiter and other planets as well. And the basic process that happens is more or less the same. As I was telling, that this is a picture of the International Space Station. You can see in the right side of the diagram, this y-axis is the height, and the x-axis is the month in the year of 2018 and 2019. And you can see that if you leave the space station at a particular orbit, it actually decays down with time. And then you require a boosting, and to take it up. You require a thrust of air to take it up to a higher height. And then again, if you leave it there, it will decay, it will lose the orbit, it will come down, and again you have to take it up. This kind of satellite operation or maintenance, orbit maintenance, goes on continuously. But the point here is that The reason why it decays is because of something called the drag of the atmosphere, even at that height, where it, because of that drag, because of the enhanced drag, it can come down. And when space weather disturbances are there, it increases the drag. And as a result of which, the orbit maintenance of different satellites that are there at different orbits, at low Earth orbiting satellite, that becomes very crucial at that place, at that time. You have heard about loss of SpaceX Starlink satellites, which had happened in February 2022. And interestingly, 39 satellites, or 38 or 49 satellites, it was lost because of these changes in the drag, because of a storm or solar storm that has happened. And going by the model, by the empirical model, when scientists in the company Tesla, they estimated the drag, they used something called an empirical model, which is not a physics-based model. That means it puts some value based on past observations, some value here, and it extrapolates somewhere else. And if it puts those values, it actually underestimated the impact of the solar storm on the upper part of the ionosphere, and as a result of which the drag calculation was not correct. And this paper shows that if you calculate it with respect to the physics-based model, it can actually estimate the drag correctly. And therefore, it shows that it is very important for space weather evaluation. Sometimes if smaller solar disturbances can create a greater impact, and sometimes it's greater solar disturbances, for reasons which needs to be understood, it can create a smaller impact as well. And therefore, this forecasting of space weather is of utmost importance, because we have a lot of technological assets. For example, satellites and other technological assets are there in space, and it is important that space weather forecasting has to be as accurate as possible to take a preventive measure, so that we don't lose these national assets during this kind of events. You also have a radio propagation navigation that is affected when space weather events are there. It is because ionosphere, these radio beams, which are at different heights, some of them are geostationary height, like for example, Indian Regional Navigation Satellite System, or NAVIC, which is there at geostationary and geosynchronous orbit. And this satellite sends the radio beams which come through ionosphere, and these ionosphere's plasma, which is there, can become turbulent on occasions, and creating, when radio beam passes through that, it is actually bends, and it doesn't reach the receiver the way you expect it to receive, and therefore there is an error in terms of estimating the position of any navigation purpose or communication purpose. So for navigation over the polar region and other places where the ionosphere is extremely turbulent, airplane navigation and other things, this is an important factor that is taken care, needs to be addressed when ionosphere becomes turbulent due to solar disturbances. Now, space weather impact also depends on the type of planetary atmospheres. For example, Earth is a nitrogen-rich atmosphere. If you go to Venus and Mars, it's a carbon dioxide-rich atmosphere. And if you go to outer planets, it is hydrogen and helium-rich atmosphere. Now, why it is important? Because the solar wind, when it comes, it actually hits the atmosphere, outer part of the atmosphere. And therefore, the composition of the atmosphere plays a very important role, so that what kind of ionization will exist, what kind of ions will exist, what will be its impact of the solar wind when it is impacting the upper part of the atmosphere, how the ionization will vary. That becomes a crucial factor to be considered when we want to assess the importance of space weather on any planet, let alone Earth. So ionosphere, as I was telling, is the upper part of the atmosphere where sufficient charged particles exist, and so that it affects the radio propagation. And there are different layers in the ionosphere, and because of the solar disturbances, when these layers the plasma becomes turbulent, it can affect VLF communication, HF communication, or any satellite communications as well. Now, if you go above the ionosphere, for example, beyond 1,000 kilometers of height, you come across a huge region of space which is full of tenuous plasma. The plasma is not, the density is not that much, but the motion of the plasma is completely governed by the magnetic field of the Earth. As you know, Earth has a magnetic field which is primarily dipolar, and this dipolar magnetic field doesn't look like dipolar because of the solar wind. On the day side, it is highly compressed. On the night side, it is highly elongated, and therefore it gives us a look of appearance of this type where day and night sides are asymmetric. It is because solar wind flows this way, and the magnetic field, which solar wind magnetic field, which gets connected to this magnetic field, they actually take the Earth's magnetic field to the night side, stretching it to a great extent on the night side, and that's how magnetospheric cavity looks asymmetric. It is a lifesaver for us, and the evolution of life on Earth is possible because we have a magnetic field which doesn't allow direct entry of charged particles coming from the solar wind into the Earth's atmosphere and on the surface of the Earth, preventing us from allowing us to survive on this planet for such a long duration of time. And therefore, magnetic field is very important, and research shows that the magnetic moment of the Earth, this is a model estimate which shows that the magnetic moment of the Earth is decreasing over a period of time. And what is its not only it is decreasing, but the magnetic pole on the northern side is actually moving from Canadian side to the Siberian side. So if you look at 1900 to 2020, you see it has moved from Canada to Siberia, which is a huge movement. Even if you look at the deep equator, which is where India is and where we are living in, there also you can see the deep equatorial movement. Of course, not to this extent, but there are movements which is seen in the 100 years of time scale. And therefore, it is important to consider the evolution of magnetic field, the change in the magnetic field, for the survivability or sustainability of mankind on the planet, because this magnetic field acts as a shield to those energetic particles coming out from the sun during the sun is disturbed. And modeling studies shows that a typically dipolar kind of a magnetic field, actually wherever is North Pole is there and South Pole is there, it is not always will remain at the same position, but the ice core data and other data shows that in the past, this magnetic field has flipped. The polarity has flipped. South has become north and north has become south. And in between this polarity reversal, there comes a period when Earth didn't have a dipolar magnetic field configuration. It has had a multipolar magnetic field configuration. And at that time, you can easily guess the kind of interaction it will have with the solar wind will be very different than what you encountered at this point of time. So therefore, it is very important to track the evolution of magnetic field in the context of space weather assessment and forecasting. Different planets have different kind of magnetic field. For example, to give you an extreme example, if you look at the Uranus, here the rotation axis of Uranus, and if you look at the magnetic axis of Uranus rotation axis is in the plane of the sun and the planets, which we call the ecliptic plane. This is in the plane, and it is actually rolling on that plane. Whereas magnetic axis is this way, and the magnet that lies inside, if you consider it is as a dipole, is not at the center, is off center. So the kind of interaction it will have, space weather disturbances it will have because of the solar disturbances will be very different than what we encounter on Earth. So it depends. The kind of space weather impact you will see, it depends not only on the solar wind, but also on the kind of magnetic field geometry you are having on a particular planet. So it is very, very important to consider both the aspects in order to have the perfect assessment of space weather. Therefore, three primary goals of space weather research, and as you know that impacts of space weather are manifold. It can affect navigation, it can radio scintillation, it can solar cell, it can damage. If you have astronauts floating around and repairing spacecraft, having spacewalk, they can get affected because of high energy radiation coming from the sun during solar flares. You have satellite which are undergoing drags, and then it can decay its orbit, resulting into the loss of satellite sometimes, the way it has happened for the Tesla satellites, Starlink satellites. It can affect the navigation system, electric grid disruption, telecommunication, and all kinds of technological systems it can affect. Therefore, three primary goals of space weather research can be defined as follows: that do we understand the space environment that we live in, and can we predict the solar disturbances, and can we assess and forecast the impact? And therefore, the whole space weather research community is actually focuses on these three aspects so that we have a better understanding of the sun-earth connection and near-earth space environment. Driver of the space weather, naturally, as you know, it is the sun, or in Sanskrit it's called Aditya, and it affects the earth in three different ways. One is magnetic field, one is radiation, another is particle. If you look at the magnetic field, there are coronal mass ejections that are coming from the sun, as you can see here. These are magnetized plasmas which are thrown into space, which are hugely large, and that can come and hit a magnetized body like Earth, and that can cause disruption in the outer part of the geospace. You have co-rotating interaction region, or stream interaction region they call it, where the slow wind from the sun and the fast wind from the sun, they can interact in the space, and they form a region where it's called interaction region. And that interaction region magnetic field can be very turbulent, and if it is crossing the Earth's orbit, then you will have this perturbation in the Earth orbit as well. And therefore this is called, and this whole structure is rotating with respect to sun, and if it comes back, and then it's called a co-rotating interaction region or stream interaction region. Therefore magnetic field polarity is very important, and if the southward magnetic field in the solar wind exists, and because Earth has a northward magnetic field, then it's a perfect recipe for disruption. And because under that condition of opposite polarity, there can be magnetic marching or reconnection that can happen, allowing the solar wind magnetic field to disrupt the terrestrial magnetic field and reconfigure the Earth's magnetic field under those circumstances. And there are radiations where sun has solar flares, where huge number of suppose if you combine millions of atomic explosion, nuclear explosions, that you do it simultaneously, allow it to happen simultaneously, what you get is a solar flare. And this solar flare, when it happens, it can give a lot of X-ray radiation or extreme ultraviolet radiations. And these radiations are very harmful because the radiation X class or UV radiations, they increase manifold. And if there is a, generally if you are on the ground, these radiations are blocked by the atmosphere. But suppose if you are in the on a space station, and an astronaut is coming out for space work, and this kind of flaring events happen, then the radiation dose on that astronaut will be very, very high, resulting into very damaging consequences in the long run. And these are solar flares, and there are different classes of solar flares, which is X class is the most strongest solar flare, and the B class is the weaker or solar flare. So this is how it is. In terms of intensity, these are one order lesser and lesser intensity that is coming from the sun during these classes of flares. Then there are particles. When I say particles from sun, continuously solar wind is coming, and also energetic particles are coming from the sun all the time. During disturbances, this intensity increases to a great extent. And these particles can be of three different types. One is the slow and fast solar wind particles, where energies range up to 3 kilo electron volt. Then from 3 kilo electron volt to hundreds of kilo electron volt, which are called suprathermal particles, which is here. Here it is slow and fast solar wind. And then even if you go still higher energy, you have solar energetic particles, or SEPs. Now these particles, one feeds the other, and it is important to know about the origin and acceleration or energization of these particles so that we can understand their impact on the terrestrial upper atmosphere. Having said this much, this is a typical example of how a geomagnetic storm happens, where the solar wind magnetic field is this, represented by this. It has an opposite polarity of the Earth's magnetic field. It gets connected here, it drags it to the night side, and then there is a reconnection which takes place. Once it is reconnected, the magnetic field converges towards the Earth, and as it comes, it actually feeds the current which is flowing at this height, at a height of 6 Earth radii or 36,000 kilometers. And if you have a magnetic measurement on the surface, what you will see that the current on top of you has increased, which we called as ring current, because it is encircles the Earth at a height of 36,000 kilometers. This is a typical sequence of a geomagnetic storm that can happen, and it starts from the polarity of the solar wind magnetic field. Then there is something called magnetospheric substorm, which can happen on the night side of the magnetosphere, because when storm happens, it actually stretches the magnetic field, so magnetic energy is stored there, and any disturbances in this region can actually release that energy. Therefore, magnetospheric substorms is not driven by storm, is actually triggered by, it can trigger substorm, but it is not driven by storm. Storm only deposits the energy, but when and how much to be released, that energy to be released, that magnetosphere decides. And solar wind parameters like density or velocity change, they can, or magnetic field change, they can only trigger the substorm, but they cannot control it. So substorm is a process of magnetosphere intrinsically. It is triggered by storm, solar wind parameters, but it is not maintained by solar wind parameters, because once it is triggered, magnetospheric substorm can go on their own. So it has its own decisive capacity, which it decides that when, how much, and how long this energy has to be released into the ionosphere of the Earth. Now, having said this much, the last 2-3 slides I'll tell that because of these damaging consequences, and from the application side, and in order to understand the space weather from the physics point of view, we need observation, we need to understand the solar wind before it hits the Earth. And therefore, Sun-Earth Lagrangian point, first Lagrangian point, which is where the gravity between Sun and Earth almost balances out, there we can place a satellite which can observe the Sun without any eclipse which is what happens in any earthbound orbit, because there it is very difficult to have 24/7 observation of the Sun without having any eclipse. And because it is outside the Earth's magnetosphere, it can sample pure solar wind, as you don't have the concentration or the sample from the Earth's magnetosphere. And then another point is, if you take the typical solar wind velocity of 400 km per second, L1 point is almost an hour away. So measurement from L1 can help in making space weather forecasting models. This may help in preventing damage to space and technological assets in the long run. And so Aditya L1 is India's first observatory class dedicated mission from India for solar and heliospheric studies. And it's a science mission whose objective is to understand the Sun and the solar wind in a much better way, but it will also cater to understand some of those space weather forecasting tools, or formulate some of the space weather forecasting tools in the long run. So this is already at the L1 orbit and giving a very good data set on which the scientists are working on to bring out various aspects of space weather coupling between the Sun and the Earth. We are also planning one more mission which we call Disha, and once you measure the solar wind disturbances from L1 point, we also want to see what is the impact on the ionosphere, where many satellites, the low Earth orbiting satellites, they move. And in order to do that, it is proposed that we have 2 satellites in 2 different orbits. One is high inclination and another is low inclination. And these 2 satellites will have various measurements, which is listed below, so that we are able to evaluate and make an assessment of corresponding to what kind of disturbances, what impact the ionosphere will have or thermosphere will have, and so that we can make better not only understand the physics of it, of the sun-earth coupling, but also to make better forecasting model. So with this, I thank you for your attention. And space weather is an important arena where India is going in a very, very strong manner with the launch of Aditya L1. And future missions are also being planned to understand this domain of science and application in a much more comprehensive manner. Thank you so much for your attention.